Okay, we're going to look at another example of a double integral over a region. So we first of all want to think about whether we would prefer to do this as a dx integral on the inner integral, as a dy integral on the inner integral, or maybe in polar coordinates. So let's look a little bit at the region first of all. So if we think about this region and think about whether the region is x simple or y simple or r simple or theta simple, let's start with x simple. So if you think about this region, you should be able to see that it is not x simple. If I go through the region, I don't want to draw on it because we're going to draw some other things here, but if you go through the region in the direction of increasing x, sometimes you enter along this inner arc of a circle and leave through this outer arc of a circle, and sometimes you leave through the y-axis, this line, and leave through the circle. So it is not x simple. That doesn't mean we could not do the integral with respect to x on the inner integral, but it would mean we would need to split it into two separate regions where we go through one region on one integral and then different region with x dx on the inner integral for the second region. Same for y. This region is also not y simple. If I go through this region in the direction of increasing y, sometimes I enter through this inner circle and leave through the outer circle, and sometimes through this line and leave through the outer circle. So also not y simple. So let's talk about x and y and think about the function, integrating the function with respect to x or y. So if I were going to integrate this function with dx on the inner integral, I would be thinking about this as e to the x squared plus constant. I could perhaps use a property of exponents. A to the m times a to the n is a to the m plus n. We have something of this form, and split that up into e to the x squared times e to the y squared. But any of those integrals, e to the x squared plus constant or e to the x squared times something else, you should say, I don't really want to do that integral with respect to x. That is a non-elementary integral, and we require a Taylor series in order to set up that integral and do that integral. So if you didn't already recognize those as non-elementary integrals that you would prefer not to do that way, you need to start recognizing that now. So not only is the region neither x simple nor y simple, but the function is not easy to integrate with respect to x, or because x and y are symmetric here, or with respect to y. So this function also is not easy to integrate with respect to y. So this problem is very difficult if you're in x and y coordinates. It is screaming polar coordinates at you. This problem is screaming polar coordinates at you. So we will convert this to polar coordinates, and you will see how simple this problem actually becomes in polar coordinates. And we'll talk about what parts of this problem here are screaming polar coordinates at you. One of them is the region. When I convert this region to polar coordinates, this is a polar rectangle. This is a region that is completely made up of boundaries that are constants in polar coordinates. So these are both circles. One has radius 1. The equation for this circle in polar coordinates is r equals 1. This circle has radius 2. So in polar coordinates, that circle has an equation r equals 2. So we have constants. If you just think about polar graph paper, these would be along the grid lines of polar graph paper. And then if you think about sweeping through that region in the direction of increasing theta, we start here at theta equals 0, and we will leave here on the y-axis at theta equals pi over 2. So theta equals 0 is here, and theta equals pi over 2 is here. So this region is completely along grid lines in polar graph paper. We would think about that as a polar rectangle. So this region is very simple in polar coordinates, and actually the function is also much easier to deal with in polar coordinates. So let's think about converting the function to polar coordinates. We do have something that we need to remember about the dA. If we're going to do an integral in polar coordinates, we'll set up the limits of integration and actually go ahead and do the integral. All right, so this problem again is screaming. I don't want to scream at you in the video, but it is screaming polar coordinates at you. partly because of the region and partly because of the function that you want to integrate. All right, so when I convert the function to polar coordinates, we've got x equals r cosine theta, y equals r sine theta, but you also have the conversion formula x squared plus y squared equals r squared. So we end up taking this expression here that has two variables, and we end up condensing that to an expression that has only one variable. And at first that might still seem very difficult because this is also a non-elementary integral with respect to r. But the other key thing to remember here is that with that dA in polar coordinates has an extra factor. And in this problem, that extra factor is actually what makes this integration turn out pretty easily. So remember that the dA has that extra r in there. It's very easy to forget it. It's based on the geometry of the polar rectangle, the area of that polar rectangle. But the key thing here is to remember to put it there. And then this integral is actually very easy to do with respect to r or theta. Because this is a polar rectangle, it doesn't matter whether I do dr or d theta on my inner integral. All of these limits of integration are going to be constants. I'm going to go ahead and just do r on the inner integral and theta on the outer integral. So when I go through the region in the direction of increasing r, I will enter the region. Here's r equals 0, but I'm not in the region when I'm here. I'll enter the region when I get to this curve, which is r equals 1. And I leave the region when I get to this circle, which is r equals 2. I don't need to write r equals there, but I can if I want to remind myself what those values are. And then theta will go from 0 to pi over 2. Okay, so I'm going to go ahead and do this inner integral. This one is a u substitution. I'm going to go ahead and write it out this time since I have some space. It's perfectly fine if you can do that u substitution in your head. I would expect many of you by this point will be able to do that. All right, so I will let u equal r squared. And then my du is 2r dr. All right, and so this is the issue with the u substitution. This extra r that came from my dA makes this u substitution work. I have this extra 2 here I need to deal with, so I prefer to do it this way. There's more than one way to handle that. And then I'm going to go ahead and do the u substitution and put these in place. So theta still goes from 0 to pi over 2. Notice I'm not letting that disappear. That's still there. I'm going to go ahead and substitute in place of my r dr. I'll have 1/2 du, and this will be e to the u. My d theta is still there for that. This inner integral, I haven't actually done the integration yet. So there are two ways you can handle this. Remember that when you do an integral here with a u substitution, a definite integral, that you might want to convert these limits of integration to u values. You would use this. So when r equals 1, u is also 1. But when r equals 2, u would be 4. So you can put a 1 and a 4 here. I prefer to usually just leave them, but then they need to be labeled. R equals 1 to r equals 2. If you just write 1 to 2 with no labels there, then the 1 to 2 would be u values, and that would technically not be correct at that step. Okay, so here I'll have 1/2 e to the u for my 1/2 e to the u. So I have e to the u. I'm going to go ahead and back substitute for my u is r squared, and that will go from 1 to 2. I'm going to go ahead and put these numbers in. So I'll have 1/2 e to the 4th minus 1/2 e to the 1st. Okay, and I wanted to say something about this particular problem. This is part of why I wanted to work this problem out too. So sometimes I'll see students look at this as two separate terms, integrate with respect to theta, and put all that stuff in separate terms. But the other thing to notice here is that this is all just a great big constant, kind of a messy constant, but all just a constant. And so I can just keep that as one unit here, and maybe even put the whole thing over 2. So I'll have e to the 4th minus e to the 1st, or e all over 2. So I have that whole constant, and then times theta, where theta will go from 0 to pi over 2. And this is another place where if you kind of have done this a couple times, you might notice there's some things that just always happen that allow you to sort of shortcut some things as you do problems later. It's a little bit of a time-saving thing. So I have this whole constant times theta, and theta will go from 0 to pi over 2, so I'll have that whole constant times pi over 2 minus 0, or that whole constant times pi over 2. So I'll have e to the 4th minus e all over 4. So if you kind of notice what's happening there, you might be able to go from this step all the way to the end without necessarily having to write that out. Noticing you have this whole constant. You're going to get that whole constant times theta subtracted from these. So you're just going to have this whole constant times the difference between these two values. So that can save you some time when you're doing some problems. Sometimes the double and especially triple integrals can get kind of long. So especially if you can shortcut this part at the end, that's a little bit nice there. So again, one more thing before I leave this problem, why this is screaming polar coordinates at you. The region is a polar rectangle. Simple in polar coordinates, very difficult in xy coordinates because you have to split it into separate regions. The function turns out pretty easy to integrate in polar coordinates, extremely difficult to integrate in rectangular coordinates. In general, this x squared plus y squared in a function often turns out nicer when you change to polar coordinates. You can't say 100% of the time because it depends exactly how the x squared plus y squared is in there. But when that's in here like this, and that u substitution then works nicely, and I have this region, that's why this problem is screaming polar coordinates at you. When we get to an exam, I expect that without being told what kind of coordinate system to use, you know that a problem like this would be much easier to do in polar coordinates, and you just go right there so that you don't waste a lot of time trying to do rectangular coordinates when that's not really a good strategy for this problem anyway. You'll find in a lot of the textbook homework that they tell you to convert to polar coordinates, but you need to be paying attention to what are the key features that would make that problem work better in polar coordinates and why you would want to convert to polar coordinates even if it doesn't tell you to do that. Okay, we got a couple more examples of double integrals in polar coordinates and then dig into your homework.